Okay, so the second question here talks about the buffer range at which the pH can become effective, right? We know is from 0.1 to 10, right? In order for it to be effective. So the rate that we're talking about the ratio of our base to our acid, right? So use the Henderson-Hasselbalch equation to determine how far away the pH of the buffer can be, plus or minus from the pKa of a weak acid. Your answer represents the normally accepted range of the buffer. Okay, so let's take a look at the original equation. pH is equal to pKa plus log of our ratio, right? All right, so the buffer range, so let's take a look. Let's assume that we have a certain ratio here. So we're going to go from, we want the plus or minus maximum it can be. So we're going to do this once by putting the ratio in as being 0.1 and do it again with the ratio of being 10. So the pH is equal to pKa plus the log of 0.1. So the log of 0.1, if we were to do this in your calculator, you would have -1 as your answer. Let me just double check on that. Yes, -1. So that means the pKa would be, the pH would be equal to pKa minus 1, right? Like I've just replaced the log of that. So if we were to do this exact same thing, but place the ratio of being a log of 10, imagine that spelled log properly. So log of 10 is actually +1. So this would be pH is equal to pKa plus 1. So that actually gives us the range of our buffer. So the pH range where we have that effective resistance would be from a pKa plus 1 to -1. So let's say, for example, the pK, I'm going to give you an example here. So this is the correct answer, but let's put in a number. Let's say the pKa of a weak acid was, 2.75. Okay, so that means that the resistance range that that weak acid would be able to do would be between pH of being 1.75 to 3.75. So like plus and minus 1 from what the pKa number is. So what that means is if it were to go below that value or above this value, you are no longer in the buffering range of that buffer. So meaning outside of that range, you will have a drastic change in the pH outside of that. Obviously, ideally would be to have a log of 1, right? Remember when the ratio is exactly 1, that means that it would be equal to your pKa because the log of 1, of course, is 0, which would be dead in the middle of this. Okay. And our last question here, so this is saying, so prior to being used to measure the pH of a solution, pH meters are often calibrated with solutions buffered to pH of 7, pH of 4, or a pH of 10. Use the table of relative strengths of acids and bases, which is in your textbook, and the Henderson-Hasselbalch equation to select 3 appropriate conjugate acid-base pairs that could be used to buffer these solutions. Okay, so if our desired pH is 4, okay, sorry, pardon me, I had to pause the video for a second there. So what we would have to do here is we want to pick something that has the pKa closest to the number of the desired pH. So remember that the Henderson-Hasselbalch equation, log of our base over our acid. So remember the best case scenario to have the pKa, like your buffer being the best, most efficient as possible, would be to have a ratio of being 1, right? So pH is equal to pKa plus the log of 1, which would be basically 0. So in other words, pH is equal to pKa. That's like the optimum option. So what we would do here is we want to find something. So imagine we want a pKa of 4. So what we would do is we would want to look and find what the Ka value is that would be closest to give us this. So to figure out the Ka value, remember P of anything, to go in the reverse, you can do 10 to the negative pKa to give us the Ka value. So if we do 10 to the negative 4, we can solve for what the Ka value is that we want to actually ideally look for. So let's do this. So let's do the first one. So 10 to the negative 4 gives us a value of course, 1 times 10 to the negative 4. So we would look on our table, and actually I'm going to try and pull it up here so we can do this at the same time live. Just give me a second. Don't you love that? Okay. So let's take a look. We need our weak acid chart. These are KSPs. All right, so here we go. So we want to find something that has, let me zoom in a bit. Okay, that has a value of 1 times 10 to the negative 4. Okay, so there's nothing that is exactly 1 times 10 to the negative 4, but we have two options that are kind of in between. So we have 1.5 times 10 to the negative 4, or we have 6.5 times 10 to the negative 5. Those are kind of like the closest two numbers to what we want. So to double check which one would be the best choice, we can do the negative log of each of these. And whichever one gives us a pKa closer to 4 would be the winner, the best one. So the chromium ion has a Ka value of 1.5 times 10 to the negative 4. So if we take the pKa of that, so negative log of 1.5 times 10 to the negative 4, that gives us 3.82 for our pH, right? Because remember that the best one we can get is if the pH is equal to the pKa, right? So the one that is the next closest is benzoic acid. So benzoic acid has a Ka value of 6.5 times 10 to the negative 5. So the pKa value there, so we have a negative log of 6.5 times 10 to the negative 5. The pKa value there is 4.19. So actually between the two, even though they're very close, one is, am I doing that right? One is 8.18 off and one is 0.19 off. So ideally, to be honest, the back of your book gives your benzoic acid as being the closest one. But I would argue and say that I think that the chromium ion would be a better choice. I mean, they're very close. They're almost equivalent in how far off they each are. But let's say we had here, in this case, literally, like I'd probably accept either one. It's not very different. Let me double check. Let me do the next level of significant digit here. I'm curious. So this is 4.187. Let's get even more specific to see which one is the which one is the winner. And this is 2, 4. So we have 0.187. So one is, this is a difference of 0.183. 183. Pardon me, sorry, 0.187. And that is a difference of 0.176. So actually, the chromium ion is closer to the number 4. So even though your textbook answer key says benzoic, I'm gonna argue on that one and say that it's the hexaaquochromium ion, or I'm just gonna put in here the chromium ion. So the conjugate base, so the pKa value, we have this here. It was the 3 point, we wanted it to be as close to 4 as possible, but it's 3.82. Okay, so then the salt of that, the chromium ion, is a CrH2O6 positive 3. So I'll do the formula for that here in case you forgot. Right? So the formula here for the conjugate base, we want a conjugate base salt of that. So I would do CrH2O5OH. That's a positive 2. So you have to remember when you add in your chlorine, it's going to crisscross with a 2. Right? Because it goes from +3 to +2. All right. Okay, so let's do the next one. Okay, so we're going to do the same thing, but now our pH values are going to be different. So we want a pKa value of as close to 7 as possible. So we're going to do 10 to the negative pKa. So we want 10 to the negative 7. So we want to find something that has 1.0 times 10 to the negative 7 as its Ka value, right? So let's go here. 1.0 times 10 to the negative 7. So here we have one that is bang on, so there is no question about that. So that is going to be our hydrogen sulfite ion. That's going to be our weak acid. So that one was easy enough for us. So over here we have our hydrogen sulfate. So pardon me, it's sulfite, which is HSO3. -1. And then the pKa is actually exactly 7. So the acid, the salt of the conjugate base is going to be our, we can put sodium with it, so sodium sulfite. And it'll be a 2, because it will be -2 afterwards. All right. That was a good one. So we're going to do the same thing, except now we're going to do it with a 10. So we're going to get our Ka value is going to be 10 to the negative 10, which is going to be 1 times 10 to the negative 10, of course. So we want to find something that is 1 times 10 to the negative 10. So it looks like the closest one that's here is going to be phenol. To be honest, just by looking at the other numbers, this is going to be, it's very close to being 1. So we have here 1.3 times 10 to the negative 10. So if we do, let's double check that. So to get the pKa, if we do negative log of, I forgot the number already. Let me look this up again. That was our phenol, 1.3 times 10 to the negative 10, just to get our Ka value. 1.3 times 10 to the negative 10. So this value here is 9.89, so very close to 10. And then that is going to be our phenol, which is C6H5OH. And then over here, it's going to be C6H5O -1, so we're going to put that with a spectator ion salt. Okay, so that is it for section 6.2. So I know that was quite lengthy. The last portion talks about the maintenance of blood pH, which our blood maintains using a buffer, which you would have learned if you do take or if you've taken grade 12 biology. So it's quite interesting, the worlds of chemistry and biology coming together. All right, have a good day.